So the students, we have just finished our discussion on single variable, and now let's move to partial differentiation, which is mainly defined for several variable function, mainly minimum two variables. Okay, so we have just discussed about for single variables, and now we have to consider two or more than two variables. So let me take initially for two variable function. So let me take z, which is a function of x and y. Okay, f of x, y. We have function of two variable of x and y, and if we take the differentiation of z with respect to x, okay, so here we can take differentiation in two ways. Once when we can take differentiation with respect to x, then we like to keep constant y, and when we will take the differentiation of z with respect to y, then obviously we will take x as constant. So two possibilities are there, and these kinds of derivatives, when the differentiation is taken with respect to only one variable, treating as other variables constant, is known as partial differentiation. Okay, so if we take the differentiation of z with respect to x only, in that case we can write it like this, that del z over del x. Okay, so or you can write it, if we write this function, this is sometimes we can treat z as a function of xy, and sometimes we can write f as a function of xy. So in physics this kind of notation is more useful. Okay, sometimes in physics most of the cases we use this kinds of notation, f is the function of x and y, but in mathematics you can see this kinds of notation, that z is the function of x, y, or something else. Okay, like in single variable case, in mathematics always we like to represent a function y is equal to f of x, but in physics we like to represent this like f is equal to f of x. So these are just notation. Okay, so in physics we like to denote the function in this way. Okay, in this way. So we can take del z upon del x, or differentiation of z with respect to x, only x, when y is fixed, or if there is also another variables, then all the variables are constant, only the variable is x when we take the differentiation of z with respect to x. Or we can denote this like del f del x. If we denote this, then we will take del f upon del x, or you can simply write it as fx. Okay, or sometimes it can be written as like this also. But this kind of relations, this kind of notation is more useful and frequently used. Okay, this kinds of notation or this kinds of notation. Similarly, if we take the derivative of z with respect to y, then del z over del y, or you can write it as like del f upon del y, or you can write it as fy, or you can write it as dyf. So these all are the notations. Okay, and we can write the definition also, as we have written the definition in case of single variable function. So here we also can define this del z upon del x like this. We can here define this. Okay, there is the same formula, but only the notations are changed, but the definition will be same. And here when we talk about the del z over del x, okay, then we have to write like this. So the partial differentiation del z upon del x is nothing but limit del x tends to 0, we can write it as like this, del x tends to 0, f of x plus del x, x plus del x and y minus f x comma y divided by del x. As we have written, when we have f is equal to f of x, and when we take derivative for single variable, we have written that, let me take more space, okay, so that you can understand, you can compare actually, okay, with the single variable function, then your understanding will be so easy. So let me give you that kind of thing. Okay, so if we talk about for single variable, then what we have defined there, for single variable, that if we have a function f and if we take df upon dx, so in that case we have written like f of x plus del x minus f of x divided by del x and limit del x tends to 0. We can write this kind of situation. Okay, so similarly if we compare this, the expression is same, only different is here the differentiation with respect to x, total differentiation of f with respect to x, and as this is the single variable function, so we have used only x plus del x and f of x, but here the original function is f of xy, so instead of x we have written xy, but at the differentiation is with respect to x, so only change is x, so x plus del x I have written here. Similarly, if we take the differentiation of y with respect to x, a differentiation of z with respect to y, then we will have del z upon del y, and in that case what will be the relation? Relation will limit delta x tends to, so delta y tends to 0, and it will be f of x comma y plus del y, okay, minus f x comma y divided by del y. So you can see the expressions are same. If you can see the expressions, all the expressions, okay, the pattern of the expression are same, but instead of one variable, here is two variable involved. So once we like to change y and once we like to change x. So when y changes, then x is fixed, you can see, but and when x changes, y is fixed. So this is the main significance of this partial differentiation, that when we take the differentiation with respect to one variable, then other variables remains constant. And just like single variable case, that if we have a function f, if we take the derivative, that is the del f del x, sorry, for single variable function always we have taken df dx, okay. So as for single variable you can take, so if we have a function f which is a function of x and is just a single variable function, then if we take differentiation, first time differentiation, that was df upon dx, and if we take differentiation again, then we have d dx of df dx, and that we have written like d2f dx x2. Similarly, if we have a partial differentiation of f, when we have function of two variable, that is if f is f of x comma y, that is function of two variable, so in that case I have said earlier, if we take first time differentiation with respect to x, then it will be del f upon del x. Now del f upon del x. Now here two possibilities are there. Again, when we want to take the second time differentiation, this is the first time differentiation del f over del x, or we have the first time differentiation, that is del f over del y. These two are possible. But if we want to take the second time differentiation of del f del x, then we have two possibility, that one is with respect to x and one is with respect to y also. So we have two possibility here. Similarly, here also, if we take del f del y, okay, del f del y, then we can also here take differentiation with respect to y, as well as we can take differentiation with respect to x also. So this can be written as del 2f del x2, and that this can be written as del 2f del y del x. This can be written as, can you see, del 2f del y2, and this can be written as del 2f del x del y. Okay, so this is the main things. So this there is some notation also for this. Let me take the notations. This can be written as f xx. Similarly, this can be written as f yy. Okay, and this can be written as f, that is del 2f del, this is written as del xy. Okay, this is xy and this is yx. So please remember with the notation that when if we denote this as if xy, then it will be yx. So notation is reverse. Okay, so if we have del 2f del y del x, then we have denoted this thing as f xy, and if we have del x del y, then we like to denote it like f yx. Okay, so these are the notations and some basic things about partial derivatives. And in all ordinary case, you can easily prove that f xy is equal to f yx. In all ordinary case, you can see that f xy is equal to f yx. Okay, so now let me solve some questions that so that your concept will be clear. Okay, how to operate this you should know. So let me take some problems. Okay, so let me take the first question. So find the first and second partial derivatives. Find the first and second partial derivatives and second partial derivatives of the function where the function is given that z is equal to x cube plus y cube minus 3axy. Okay, so we have to take first partial derivative and second, all the possible first and second partial derivatives that we have defined earlier. Okay, so just defined all the things. So let me take first time differentiation. So if we take del z over del x, then it will be 3x square, and the differentiation of y cube will be 0 because y is taken as constant here. Okay, we have to take constant of y. So y is just act like a number. Okay, so the differentiation of y will be 0, but here the differentiation of x will be 1, so it will be minus 3ay. The constant term will be 3ay. Similarly, if we take del f del y, then you will get, from here it will be 3y square, and from here it will be 3ax. Now if we take again take the differentiation with respect to x. Okay, so then we will get del 2f del x2, that will be 6x, and the differentiation of this 0 with respect to x. Similarly, if we take del 2f del y2, then we will get 6y from the first term, and from the second term it will be 0. But now if we take the differentiation here with respect to y, so we will get del y of del f del x, so that will be nothing but del y of this term, that is 3x square minus 3ay, and it will just minus 3a, because 3x square will be 0, so this is nothing but fxy, second time derivative, or you can write it as like this, del y del x. And similarly, if we take here the differentiation of del f del y with respect to x, so it will be like this, and here you can see the differentiation of 3y square with respect to x will be 0, but here it will be only 3a, so it will be minus 3a. So you can see here that del 2f del x del y, which is nothing but fyx, that is also minus 3y. So you can easily see that fxy is equal to fyx, and all the possible partial derivatives I have taken here. Okay, so this is how you can solve the problems based on partial derivatives. The problems are so easy. Okay, so now let's move to next question. Let me take some other example. Okay, so let me take question number 2, and here the question is, if u is equal to, given as x square tan inverse y by x, x square tan inverse y by x minus y square tan inverse x by y, this is given. What you have to do, you have to prove that del to u del x del y is equal to x square minus y square divided by x square plus y square, and also prove that del to u del x del y is exactly equal to del to u del y del x. Okay, so let me solve this question. So here u is given, what u is given here is x square tan inverse y by x minus y square tan inverse x by y. Okay, now let me take the differentiation first with respect to y. As you have to find out del to u del x del y, so first we have to find out del u del y. So what will be the differentiation with respect to y? Okay, so with respect to y, x square is constant, but tan inverse y by x, the differentiation of tan inverse y by x will be 1 divided by 1 plus y by x whole square into 1 by x. The differentiation of 1 by y by x with respect to y will just be 1 by x, and here for this term the differentiation will be so long, and I think I should be written the next line. Okay, so it will be minus, so let me take y square first as constant, so the differentiation of tan inverse x by y will be 1 over 1 plus x by y whole square, but the differentiation x by y with respect to y will be minus x by y square, so it will be minus x by y square, because the differentiation of 1 by y with respect to y will be 1 by y square, and then if we take as plus the differentiation of y square, that will be 2y only into tan inverse x by y. Okay, so this will be the result. So let me simplify it. So del u del y will be, so here x and x will be cancelled, so x divided by 1 plus y by x whole square minus, you can see this y square and y square will also be cancelled out, so it will be minus x divided by 1 plus x by y whole square plus 2y into tan inverse x by y into tan inverse x by y. Okay, so what will be the final result? What will be the final result? So let me rub this upper line. So now let me check one time. Okay, so del u upon del y is x square, and then it will be this, and y square, this will be this. Okay, so I think everything is all right. So let me move to the next part of the solution. Okay, so the next part is, so del u over del y is equal to x divided by 1 plus y by x whole square minus plus x divided by 1 plus x by y whole square minus 2y tan inverse x by y. Okay, now if you simplify it, what it will be? It will be x cube upon x square plus y square, you can see, plus y square x upon x square plus y square minus 2y tan inverse x by y. Okay, now if we take common x here, then it will be just 1. So finally we will get, calculation is some lengthy, we have to do, okay, this type kind of calculation. So if we take common x here, it will be x square. From these two terms you can take common here x. So if you take common x, then here will be x square divided by x square plus y square plus y square divided by x square plus y square minus 2y tan inverse x by y. So this will be 1 if we add this, so it will finally x minus 2y tan inverse x by y. So this is del u upon del y. Okay, so if you put it in the next page, sorry for this inconvenience. So what we have done, we have just done that del u upon del y is equal to x minus 2y tan inverse y by x. Okay, so now what we have to do, we have to take differentiation with respect to x now. So del x of del u del y will be 1 minus 2y into 1 over 1 plus y square by x square into minus y upon x square. So it will be finally 1 minus, if we take here, so here will be x square plus y square and 2y into x square into minus y by x square. Again this x square and x square will cancel out, so it will be 1 plus minus plus, so 2y square divided by x square plus y square. Okay, so I think x minus so it will be x by y or y by x. Okay, it will be x by y, sorry, it is x by y. Okay, so this is x by y. So you can do it. Okay, just it was x minus 10 was x by y, it was okay, it was x by y. So if you take differentiation with respect to x, then it will be 1 minus 2y into 1 by 1 plus x by y whole square into 1 by y. So this y and y will cancel out, so it will be 1 minus 2y square divided by x square plus y square. So that will be nothing but x square minus y square divided by x square plus y square. Okay, so this is how we can prove this result, that del 2u upon del x del y is this. Okay, similarly you can get first del u del x, and if you again make the same calculation for x, you will get del u upon del x, you will get, just I am giving you the result, that 2x tan inverse y by x minus y, and again if you take the differentiation, it is del 2u upon del y del x, you will get the same result, that is x square minus y square divided by x square plus y square. So I have laid this thing for you as an homework. Okay, so this is how you can solve the problems of partial differentiation. The problems are so easy, but sometimes you have to make these kinds of lengthy but conventional calculation. Okay, the calculations sometimes be lengthy, but the calculations are easy actually. Okay, so these are most conventional calculation, so you can do these kinds of problems. So in the next class, I like to see more kinds of problems, and then we will move to homogeneous function. Okay, so please make practice. If you are in first time of these topics, so you have to make some practice on it. Okay, thank you.